Okay guys, let's take these questions up from last week. I feel like we had a bit of a lag here with the weekend and the way last week ended. It's too noisy in my backyard. I got Mackenzie Smith next door with Julia. It'd be funny to take the camera and walk over to the fence, but no, we're not doing that. So I'm out in my garage today. Let's hope it doesn't get too noisy with cars going by. This isn't going to take very long anyway. We only have 3 questions to take up, and I know what the answer's on here. You probably don't even think you need to take some of these up if you got them, but there's always margin notes that you can make, and you definitely want to do that because you're going to rely on those margin notes next year when you look back at this work. So I think I'm good. I got everything I need here. Pencil, calculator, got my SpongeBob ruler. Everything's ready to go. So let's do the first question. All right, so the deal with this question is it's frictionless, and that's really important. You can underline that or highlight it or whatever, because questions aren't going to be frictionless next year. You might get the occasional question that's frictionless, but chances are the questions are all going to involve friction, because that's another form of energy that you have to consider a transfer happening. One of the questions on here is like that, right? Was it question 2 or question 3? Question 2 is like that. So question 1 could have had friction in it, but they did say frictionless. So you can think of it like this. The car in the beginning as an object is going to have nothing but gravitational energy. And because it's frictionless, it's not going to lose any energy due to heat. It's going to slide down to the bottom of the ramp, and at the bottom of the ramp it's going to have all kinetic energy. And that kinetic energy is going to continue. It's going to strike this flexible spring, and it's going to squish. And in the end, the spring is going to come to an absolute rest, and it's going to be nothing but elastic energy at the very end of the question. Well, don't think like a grade 11. You don't have to do this first part. You don't have to convert gravitational into kinetic and see how fast it's going to be moving at the bottom, and then do another question where the speed energy becomes elastic. Conservation of energy works any point in a situation. Whatever you want to call the start and whatever you want to call the end is the start and the end. Energy has to be conserved. So skip this, skip the middleman. You don't need to calculate how fast it's going to be traveling. You can say it starts off here with nothing but gravitational, and it ends here with nothing but elastic energy. And in this question, that's your energy equation. You should start by writing the total energy before equals the total energy after. Because we're taking this up, I'm going to skip a line here, and I'm just going to write it like this. So in the beginning, at the top of the ramp, you have nothing but gravitational energy. And at the very, very end, when everything comes to a rest and everything's done, you're going to have nothing but elastic energy. And that's it. I mean, that's really all you need to understand for grade 12 is that line right there. Or sorry, not for grade 12, for university. Because that's the energy expression for this example, the way we're going to look at it. Then you get out your formula sheet, which you aren't going to have in university, so that's going to be one of the other challenges. And you substitute in your givens. Gravitational energy is mgh. Elastic energy is 1/2 kx squared. And because elastic energy doesn't have a mass in it, you can't cancel the mass left side, right side. So you're going to see questions now where mass is going to be given in the question. And in grade 11, mass being given was sort of frivolous, and it didn't really matter whether you used it or not, but now you will have to use it because there isn't a cancellation. Look and see what they're asking. Determine the height that the car was released from. So there's only one unknown here, and it's the h that's on the left. So rearrange. H will be 1/2 kx squared divided by gh, or sorry, divided by mg. And then you just make your substitutions and convert any units that you have to. I see that the compression here is in centimeters, so we'll have to convert that. 1/2, the K value is, where is it, 4,900. Be careful, you might have thought it said 900. 4,900 newtons per meter. X value needs to be converted. So don't write down 22 centimeters, write 0.22 meters and square it. Divide by the mass, which is, oh sorry, I'm off the screen a little bit. Divide by the mass, which is 5 kilograms, and G value, which is 9.8 newtons per kilogram. And university is going to get you to work out units too. You can see how this works out. Kilograms cancels kilograms. Newtons cancels newtons. Meters is going to be squared here, but then you're dividing by another meter, so that meter will cancel out with one of these meters that went after it's squared, and you'll be left with just meters in the end. And the answer's on the page, but I don't know if I rounded the answers or not. I probably did. So let's see what you would have gotten before doing any kind of rounding and just compare. No, it's 2.42, the same as what's written on the page. 2.42 meters. Okay, so let's make this question just marginally more difficult. Not really, but part B gets you to back up just a moment as the spring is being compressed. And university profs used to draw a quick set of diagrams for us to help us understand this. First, they would draw a spring with the mass on its way in, and then they would draw another diagram where the spring is completely compressed and the mass is against it and it's at rest. And then they would draw a diagram which is kind of somewhere in between, where the mass is moving, it's started to squish the spring, but it's not finished yet. It's still got more distance that it's going to squish it, and it's traveling slower. That's what we're looking at in this question. We're looking at a situation where there's still kinetic energy because the mass is still moving, but elastic energy has begun to build up because the elastic is getting squished. So there's two forms of energy at the end of the question. It still starts off in the same place. It still starts off at the top of this hill, ready to drop, and you don't need to work out any answers from part A. You can just start the question over again with this new idea and write a different energy expression now, where all the energy in the beginning is gravitational, but in the end it's splitting into two forms. There's kinetic energy and there's the beginning of elastic energy, and it's going to build up more as that kinetic energy gets continues to change into elastic energy. Fill in your given formulas. mgh, 1/2 mv squared, and 1/2 kx squared. And the unknown here is the speed of the car, so we're looking for this v right here. Now don't make the mistake of canceling the m's just because there is an m on the left and an m on the right. It's got to be in every term on the left and the right. So again, mass doesn't cancel out. And if we're rearranging for that v, that's going to be a longer expression, which is why this question, I guess, is considered to be more difficult. But it's not. I'm going to leave it written as v squared in this isolation just so I don't have to fit a square root sign on there. That's going to be a heck of a substitution, but you know, you're following this video, so let's go through it. You can sub these in faster than you can actually watch on the screen, but 5 kilograms, 9.8 newtons per kilogram. The original height was, oh, that's what we solved for in part A. I forgot. So you do need an answer from part A. You need the height because you need to sub it in right here. 2.42 meters in the beginning. Subtract off 1/2 kx squared. The k value hasn't changed because the spring constant is the spring constant. So 4,900. The compression has changed. It's only at 15 centimeters or 0.15 meters, and you're going to divide that entire thing by 1/2 the mass, 5 kilograms. And you have to root this because it's still v squared the way I have it written on the page. I'm going to do that all in one step, but let me just see what you get here for an actual answer, so that if you had some decimals you can check these out. 1/2 4,900 times, okay, divide by 0.5, divide by 5. All right, so the final answer that you get here when you square root it is 5.038, which actually doesn't round to what I have on the page. 5.038 meters per second. I actually I don't know where I lost a little bit there. I rounded it to 5.1, which would have been wrong on the page. So as far as I know, that's the correct answer, but check that out. Maybe you got 5.1. I don't think I did anything wrong here though, so maybe it, and the part A, there was no rounding involved. So check that out. Okay, so the next question. this was a good one. I hope you watch the video, otherwise it's not going to make as much sense. But there is an assumption though in this question that might not have come through immediately obvious, and the assumption is that the moment that the mass kind of hits the ground, that's when everything starts. So it hits the ground and touches down with nothing but kinetic energy. It's got no height and it's got nothing else. So it's traveling fast, and that's the entire energy in the beginning. Then it is going to begin to stretch a spring. I don't know how to really show that, but I'll sketch it on there like this. It's going to stretch a spring out. So some of that energy is going to change into elastic energy. But there's also contact with the runway and the brakes. So there's also going to be a loss of energy here due to heat, thank goodness, because the runway's not very long. And that's work. And remember, work is force times distance, whatever force you use, and whenever you use it in an energy expression like this, it's always friction. So that's what you need to understand, that diagram right there. And you need to write out a formula where all of the energy in the beginning, which is all kinetic, is going to equal the sum of all the energy in the end. Now remember, even though you kind of think of work being lost because heat goes off into the environment, it's still the sum of. So if you were to add these two things together, work and the elastic energy, that would equal the kinetic energy in the beginning. And that's it. As long as you understand that very first line, the whole conservation of energy aspect is taken care of, because the rest is just details. 1/2 mv squared is kinetic energy. Work is force of friction times distance. And elastic energy is 1/2 kx squared. Only one of these is going to be an unknown. Let's see what it is this time. What's the jet's landing speed? So we're solving for v squared again. So, well, I'll write it as v squared, and just to remind myself to root the answer in the end. You're looking at an isolation that looks like this. And all the givens are here on the page, so it's just a matter of substituting in all the information. I don't think there's anything on here that is tricky at all. The force of friction is given as a constant, so you don't have to worry about working it out. Oh, I guess there is one margin note you can make here. The distance that it takes to come to a rest and the x value, you know, these two variables here, it's not immediately obvious in the formula, but they're the same. It's called d because the old grade 11 formula for work has distance in it, and the deformation length in the elastic energy formula is written as an x. But in this rare case, the deformation length and the distance that the brakes are being slammed on are exactly the same. So we've got 1,000 newtons. The distance is 30 meters, so there's no conversion necessary. K value, 60,000 newtons per meter. And x value again, 30 meters, but because of the formula this time you have to square it. So it's weird. You don't square it here, you do square it there. 1/2 times the m, the mass is a 15-ton or 15,000 kilogram jet. And don't forget to root the answer in the end when you work it out. And let's see what we get this time in comparison to what's on the page, just in case. Hopefully those cars going by are not too loud for the video. Okay, plus 1,000 times 30, divide by 0.5, divide by 15,000. And I got to remember to take the square root because the speed is ridiculous. If you don't, you get an even number of 60 meters per second, or relatively even. There's some decimals, but rounding to 60. Hopefully you understand that. And the last question just ties into what we were doing last day, or I guess a couple days ago. You want to get around this loop, you need to analyze the conditions right here. If you're going to have the minimum speed to get around this loop, you have to at least cancel these two forces. Hopefully not just cancel. Hopefully centripetal force will be way stronger than force of gravity. But you have to at least cancel those forces if you're going to get around the loop no problem. So start with that fact. Before even looking at the energy, make sure you understand that the centripetal force must equal the force of gravity. And don't try and memorize what the result was before when we were doing loops a couple days ago. Just do it every time. you have three formulas for centripetal force. This time it's mv squared over r, the radius of the loop, and force of gravity is mg. Mass does cancel out, left side, right side, so v squared has to be gr, at least. And I'm actually going to leave it written as this, just because I've done this so many times. I know what's coming in the energy expression formula. It's going to be v squared anyway. So rather than take the root of that, I'm just going to leave it as v squared. And I'm not even going to work it out either. I mean, you could work out gr and get an actual answer, but I mean, why bother? You're going to love sticking to algebra. You just don't know it yet. Okay, but look at the energy expression here. So you are starting off in the beginning with two things. There's a compressed elastic or a compressed spring, and there's also this height. So you've got elastic energy and gravitational in the beginning. And at the end, when you're at the top of the loop, you have gravitational energy because you're up high, higher than before. And there's also kinetic energy because you must be in motion with the speed that I worked out over here on the side. So two forms of energy in the beginning, two forms of energy in the end. But hopefully you're at the point now where it doesn't matter. I mean, you could have 6 forms of energy in the beginning and 12 forms of energy in the end. It doesn't change anything. You write down your formulas, you be careful with your bed mass, and you just make sure you to watch not to make a math mistake. So two forms of energy in the beginning, elastic and gravitational. Two forms of energy in the end, kinetic and gravitational. The university profs would blow a gasket here and say that your gravitational energy can cancel out left side, right side, so you should probably indicate an initial and a final, and they prefer you have initial and final on everything anyway, just to really stress which one's which. Fill in your formulas, and you're not going to have any formulas you don't recognize ever. It's always going to be forms of energy that you dealt with in high school until they introduce a couple more in university, but no big deal. So it's all the usual stuff here. I'm going to write a little I on the H and a little F on the H just to stress which one's which. Mass almost canceled out. It would be nice, but because there's no mass in the spring energy formula, you can't cancel M, which is a pain. And the unknown here is, blah, 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 blah. What is the unknown? What's the spring constant? Oh, that's a new one. So we're isolating for K. All right, well, bring this to the other side. That'll become negative. And divide by 1/2 x squared. And actually, you know, while I bring this to the other side, I can see that there's an m in every term. I don't want to write the mass out 3 times. So I'm actually going to take it out as a common factor as I'm doing this. Excuse me. Yeah, so I'm taking an m out of every one of these terms, and I'm bringing that to the other side. So we've got 1/2 v squared plus GHF. And then I'm going to bring this over, change the sign to minus, take the mass out of it, GHI. That's a little bit shorter. I could almost take G out of the brackets too if I wanted to, but, or factor that out as just a common factor from those two, but I'll get too confused. I'm just going to leave it like that and divide by everything else on the left that was there and is getting moved over. So there's your formula, totally new formula. If you saw that in grade 11, you'd probably flip and think you were never going to understand what the heck it meant. But here you are in grade 12, going through things step by step. That should make total sense. And at this point, it's just a matter of subbing things in. The mass is 1500. You could probably sub all this in and get an answer faster than trying to watch it on the screen. 1/2 v squared, the required speed, v squared, this is back up here, v squared is gr. Actually, I should have wrote that in. I should have made that substitution while I was doing this rearrangement. You know, instead of writing v squared here, I should have just went right ahead with gr. Oh, that actually would have been good, because then we could have taken g out of the brackets. You know what? I'm going to do that right now, because otherwise there's too much writing. You want to try and minimize your writing. I don't even have a good eraser. I have my stupid SpongeBob SquarePants ruler, but no eraser. All right, if you take G out of these brackets because it is now in every term and write it out the front as a common multiple that's pulled out, you only have to write it one time. 1500 multiplied by 9.8 meters per second squared, written once, and then everything else in these brackets. So we got 1/2 the radius. Be careful, the radius is only 14 meters. Plus the initial height, 20 meters. Sorry, I got that backwards. That's plus the final height. See, this is why writing the little f and the little I is important. So let me change that. The final height is 28 meters. Subtract off the initial height, which is 20 meters. Okay, and divide by 1/2 x squared. And the x value in this question is, where the heck is it? 3 meters. Okay, so let's work all this out and make sure that the answer is going to come out correct here. I'm going to do the brackets first since it's all distance. 1/2 times 14, so 7 plus 28 minus 20 gives you 15. Multiply by 9.8 and 1500, divide by 1/2 and divide by 9. You get a whopping value in the end, and an even value, you don't even have to round it, of 49,000 newtons per meter. Now actually, because there was a value of 3 meters given in the beginning, that's one significant digit. So they're going to only accept an answer of 50,000. Especially when you do this as an online assignment. Yeah, that's not 5 significant digits. That's one significant digit with a bunch of zeros after it. Okay, that's all you need to do today. I wanted you to go through this just to sort of refresh your memory on what we were doing and hopefully take up a couple of little errors if you had any. So for the rest of this week, we're going to get into one more form of energy, because we have to before you get out of high school, and use that form of energy in some equations. So it's actually going to be very, very similar to what we just did in the last couple of days. We're just going to change the energy formulas again and look at some other problems. But the nice thing about conservation of energy, you know, this right here, the nice thing about conservation of energy is if you get it, you get it. It doesn't matter how many E's you write in the formula, and it doesn't matter how many new energy formulas you have. You just write them in, you rearrange, and you solve. And if you come to that easy understanding, you'll blow away all the people in first year university that never took 4U, because they'll have no idea what the heck's going on, and you should be able to ease your way through it. Okay, I'm going back inside, and I will post tomorrow.